Hey, so today we'll be going over this Kaggle competition for gravitational wave detection. You can see this site open over here. So first check what this competition is all about. So in this competition, you were provided with a training set of time series, a huge data set of 72 GB, coming from three gravitational interferometer, which are LIGO, Hanford, LIGO, Livingston, and Virgo. And what are interferometer? Of course, you can read all the details in this overview page over here, and there's a lot of discussion and a lot of code out there. But to brief on the interferometer is that these are extremely advanced instrument to measure the minute details of gravitational waves coming to Earth from billions of light years away. So in the data given in this competition, each time series contains either a detector noise or detector noise plus a simulated gravitational wave signal. And the task is to identify when a signal is present in the data, that is target equal to 1. So we need to use the training data along with the target value to build our model and make predictions on the test IDs in the form of probability that the target exists for that ID. So basically, data science is helping here by building models to filter out the noises from data streams. And we already know that the data stream includes both noise frequencies and gravitational waves frequencies. So we can single out the frequencies for gravitational waves with the help of our data science modeling. So now have a quick look at the data. Okay, this is the data folder, and you can see it's a huge 72.06 GB of data. We are giving a training levels and sample submissions. So if you go to the train data set, it's quite a bit of nested folder structure here. So let's see. All right, already 4 levels of folder structure, and click on this file. Okay, this is the first file, and it's a .npy file. Which is the NumPy file. And to give the basic description, we are provided with a train and test set of time series data containing simulated gravitational wave measurement from those network of 3 gravitational interferometer. And each time series contains either detector noise or detector noise plus a simulated gravitational wave signal. And the task here is to identify when a gravitational signal is actually present in the data. So each of these, there's so many, I think there are probably millions of NPY file here, and each of these .npy data file contains 3 time series. We will see in the actual notebook in a bit. So each of these .npy file contains 3 time series, one coming from each detector, and each of the time series spans 2 seconds and is sampled at 2048 Hz. And we have a total of, yes, I have the data, we have a total of 5,060,000 files, and each file is of dimension 3 into 4096, and that's how this huge data set. And now the actual Ipython notebook that I submitted for this competition. To give the overall purpose of this notebook is I wanted to implement a basic EDS to understand the overall structure of the data and also the flow of the data, and also implement simple CNN with one layer of ConvNet with Keras. This model got me a score of 0.491, or I think 0.5 or something like that, with one epoch. Which is definitely not a very good score, but that was not my intent here in this notebook, because I just wanted to achieve some baseline level of calculation with this notebook. So yeah, I will share the link of this notebook in the description for both my GitHub and in Keras and in Kaggle. All right, so first initial imports, all the regular imports, only 2 mention a special mention of this package GWPY, which is for handling specifically gravitational wave kind of data, time series and NumPy data, and also this package NN audio. This NN audio is for implementing some a spectrogram from the waves data that was given in this competition. And remember, this particular competition has 5,060,000 .npy file. And what exactly are .npy files? They are standard. These .npy files are just standard binary file format for persisting a single arbitrary NumPy array on the disk. The format stores all the shape and the data type information necessary to reconstruct the array correctly, even on another machine with different architecture. The main benefit for using .npy file is that they are incredibly fast for reading purpose compared to normal plain text or .csv files. And now initially I just wanted to check a single file, what they are and what kind of plot they produce. So I just have declared some of the variables here for the root directory, and randomly I have taken a single file here. You can say this path root directory plus train, then 000. There's 4 levels of nesting, and I'm plotting a single time series with this function get t series from file. So t series 1, I'm taking the first time series. That is, remember, each of the .npy file has 3 time series in it, coming from the 3 interparameters. So that's what I'm exactly doing here, that my first time series takes the first time series, the second one takes second, and third one and third. And sampling rate is 2048. And I'm implementing this time series function, which is from gwpy, that I have imported here from gwpi.timeseries, import time series. All right, so yeah, and this is a plot, and this plotting function is also coming from gwpy. You can see it here. Yeah, gwpi.plot, import plot. All right. Yes. So this is these times this particular graph that you can see, it's coming from one single .npy file. So each of the .npy file has this kind of data, and it is a time series plot. You can see that all of the .npy file has similar kind of time series data. And now I will be loading all the NPY files, and first take a look at the labels, the CSV file for labels that we are given. So here is the data. I am just reading the labels file, target labels file. Now we have the IDs and the target is 1 and 0. So it's a binary classification problem. 1 here means that this is a gravitational wave indeed, and 0 means it is not. And all this ID, they correspond to the file names. That is the 5,060,000 .npy files that we have. These IDs correspond to those file names. And so let's load the files. And by this code, you can check out this code. I'm using the glob module, and root directory is already defined. And from there, I am just going inside the 4 levels, nested levels of directory structure here. So within the train, I have another 4 labels, and what this star asterisk is doing is they are practically taking all the path names, all the file names from here, and storing into these variable names. And then further, with few lines of code here, I am getting the exact file path names like this, as you can see, input G2net, gravitational wave detection, etc., etc. And finally, I'm making this df train, which will become the base of our calculation going forward. So it has got just 3 columns: ID, target, and the file path name. All right, now do a simple classification first. Classification plotting. Okay, here I'm using SNS.counterplot here, and I'm just classifying the target. How many of them are 0 and 1, and it's a very, very balanced data. As you can see that it's almost equal. The 0 and 1s are almost equal. And now I'll be doing a simple EDA with the basic security analysis of the waves. Now, what is security? It's a constant quality factor transform, and it was first published in I think 1988 or so. I have actually mentioned, yeah, 1988. I've actually mentioned the original paper here. And what this does is the constant Q transform transforms a data series to the frequency domain. It is related to the frequency transform in general. The transform is well suited to musical data and proves useful where frequency spans several octaves. Now, why we are using it here is because here also we are analyzing waves data. What we are analyzing is our gravitational waves, and so all the concepts of digital signal processing or waves analysis equally apply here, because here also we'll be dealing with frequencies, wavelength, and characteristics of the waves, its domain analysis, etc. So I have put some explanation here about the CQT, and I'm also using this NN audio package, which implements this particular CQT original paper's algorithm, and it's also the most popular one to analyze audio waves and also the gravitational waves. So let's come to the calculation here. So this is our original data frame that we have just built a while back. And I have two functions here. One is get CQT spectrogram and another one is just for plotting them. So in this first function, get CQT spectrogram, I'm passing the waves of each file as the argument. And the transform I'm using here is the CQT 1992 V2. This is the algorithm that I was talking about from the original paper, and the NN audio improves it slightly or modifies it slightly, and that's why they call it V2. So all I'm doing is I'm using np.h stack. I'm stacking the waves horizontally, and here the arguments, you can see that SR stands for sampling rate, F mean for F mean, I think that's for the bin of the transform. Yes, so F one second, yeah, F mean here is a frequency for the lowest security bin. I'm just reading from their documentation, which you can find it here. This is a GitHub repository of NN audio. All right, so coming back to our function, F mean is the frequency for the lowest security bin, F max is for the highest security bin, and hop length is the hop or the strides. The default value is 512, but we are passing here as 64. And now in the plot, I am just getting, I'm just using, implementing 5 plots. So in this range of 5, I'll be passing 5 waves to this get security spectrogram function. And this is a plot that I'm getting here. Now, all right, so that was security, and then I'll also be plotting some basic KDE box plot and time series in the next section. So I'm defining a multi-plot function which will plot all the 3 of them. That is, depending on the plot type here, I am implementing both the box plot, KDE, and the time series plot as well. It is just for normal very basic checking of the data, and it's whether it's balanced or imbalanced, something like that. And normally from all these box plots and the probability distribution plot, that is a KDE plot, we can see that the data is superbly balanced. All right, now okay, that was our that was my initial EDA. I have not, now I'll be moving to the actual model building, and I'm using the Keras sequential model here. Okay, now before going into the actual model building, a quick note and word on the Keras sequential API. So in Keras, there's 2 ways to build models, which is one is sequential and another one is functional. The sequential allows, the sequential API, which I'll be using it here, allows you to create models layer by layer for most problems. It is limited in that it does not allow you to create models that share layers or have multiple inputs or outputs. So in short, you create a sequential model where you can easily add layers, and each layer can have convolution, max pooling, activation, dropout, or batch normalization. And the second way, which is a functional API, allows you to create models that are much more flexibility, as you can easily define models where layers connect to more than just the previous or the next levels, but you can actually connecting layers literally in any way that you want. So as a result, you can build much more complex models with the functional API. But for simplicity's sake, here I'll be using functional API, which pretty much is a linear stack of layers. So you can create a sequential model by passing a list of layers, instances, to the constructor. The common architecture of convnets is a sequential architecture. However, some architectures are not linear stacks. For example, Siamese networks are two parallel neural networks with much more shared layers. So let's get back to our code. Okay, so here I'm starting to build the model, but first we have to do the data generator code. And here again, why I need a data generator before I pass such a huge data of 72 GB to the model of Keras. And the key reason is to be able to handle large data with batching. So with data generator function, your RAM, CPU, or GPU does not need to handle the full data at once, which will anyway not be possible for this huge 72 GB of Kaggle data. So basically, since our code will most certainly be using the multi-core architecture of CPU, that is, it will be using 4 cores, 6 cores, 8 cores. So to take the most advantage of that, we have to make our code such a way that it processes batch by batch, and so we do not have to worry about the data generation part. Rather, we can focus on our model. So here is my data generator function. It is also very well explained in the Keras documentation, and it should, Keras documentation gives the overall architecture that this data generator function should have, and as per it, that it should have the init function, len function, get item, and this final data generation function. Out of these, I think the Keras documentation makes it mandatory to have the minimum, the len private function and the get item private function. So you can go through these in detail with the notebook that I'll be attaching in the description. So pretty much what the len is doing, it's returns the number of steps in an epoch using the samples and the batch size. And the get item method is called with the batch number, and it returns you the X and Y for this batch. And finally, the data generation is the most crucial part. So it loops through the entire data of these 5,060,000 files that we have for this data set and returns you batch by batch. So yeah, that was my data generation class. Yes, and now I'll be moving into the actual building of the model. First, a few defining some variables that will be necessary. So I need the sample submission is just this file that was given in the root of the directory. And I also need 3 sequence of data or 3 series for train, test, and validation. And that's what I'm doing here in this code, train generator for sequential model. So this is generating a sequence from this data generator function, and I'm processing it 4 things: the path, the train indices, which is my which is defined here, which is a return value of the train test split. I'm splitting all the train labels, indexes, and okay, so the train generator sequence model and validation generator for sequence model, test generator sequence model is defined here with the data generator function. And this is the actual where I'm building the sequential model of Keras. So first I'm adding a convnet and then a batch normalization, then flattening the layer, then a dense fully connected layer here with the ReLU function as activation, and then the final step, which is adding a dense layer fully connected and with sigmoid activation function. The optimizer here is Adam, and also because it's a binary classification problem, I'm using cross entropy as my loss function, and given it's a binary data structure, I'm using binary cross entropy as a loss. And if I do my model, the summary, it gives an overall summary of my data, which is printed here. And then this is the final step. I'm just running the model. Here I'm running it for a single epoch, and a single epoch and workers I'm passing as -1. That is, we'll be using how many of our CPU cores are available in the machine. So in my local machine with 8 CPU cores, it's an i7, and it ran the single epoch took almost 2.5 hours. So if you run in Kaggle with use a GPU in the Kaggle, it may run a little bit faster, but I'm yet to try that. And anyway, so this is my final model, and note that I'm using the fit generator here, and for predicting the result from the test data, I'm also using predict generator. So a quick note on this, that what is fit and fit generator, what is fit generator and predict generator, and what's the difference with the normal fit function or predict function of Keras. So in Keras, using the regular fit function or predict function is fine for small data sets, which can be loaded into the memory at once. But in practice, for most practical cases, almost all data sets are large and cannot be loaded into memory at once. So the solution is to use fit generator and predict generator with custom data generator function, which can load data to memory during the training or predicting. So basically, when you are using custom data generator, you have to use fit generator and predict generator. So so in the fit generator, you don't pass the x and y directly, unlike the normal fit function. In normal fit function, which deals with much smaller data, you just pass, it's just like an sklearn's fit function, and you pass x and y as a target variable. But in fit generator, you don't pass x and y directly. Instead, they come from the data generator function that we defined earlier above here. This function. So as is written in the Keras documentation, generator is used when you want to avoid duplicating data and using multiprocessing, and that's the case when you are also using data generator. All right, so finally, sample submission target. This is my target data coming from the return value of this predict generator function. And finally, I'm saving it in a CSV file named submission.csv, and that's what is my final output, and which I'll be submitting to Kaggle as a competition submission. I indeed did that, and the link of which I'll be sharing in the description of this video. So that was pretty much it. Thank you for watching.